Hello, this is the second part in my EMG video series. I've already finished the schematic, also the PCB. I've ordered it, started bringing it up, so I thought I'll just go over the design of my board in different sections and also do a bit of the validation of the circuitry. This is my board that I designed and manufactured. I got it manufactured from JLC PCB. They're good because they're pretty cheap. They still have good quality, which is good for a broke college student like me. As you can see, my board is pretty ugly. I think all of mine really are. I'd say I'm still pretty much like an amateur or a young player, as Dave Jones would put it, when it comes to PCBs, or maybe electronics in general. Whatever. Hopefully you can see some of the mistakes I've made, some of the good things I've done, and just learn from this. So this video is just going to focus on the power section. It's going to be really short, just because I don't want to put too much into one video. I want to go into a good amount of detail, not a good amount, but a decent amount of detail, and also I'm lazy, so before I get into the design, I'll just go over some rules I have when choosing components. So the first and golden rule is that it has to be cheap. I'm a broke college student, as I mentioned before, so I don't really want to be spending $10 on a single op amp. I'll only do that if it's absolutely necessary. If it causes the project to fail, if I don't have those specs or chip, then I'll do it. If not, I'll just go with the El Cheapos. For this board specifically, I decided to just go with surface mount components. I'm comfortable soldering surface mount components, and they take up a lot less space. And I've seen on DigiKey that they can be cheaper. They're usually cheaper. So I decided to just go all surface mount. For the ICs, I try to avoid leadless ICs, just because you have to use either like solder paste or a heat gun to solder them, and I'm not really that comfortable. I'm pretty paranoid about just cooking them, so if at all possible, I try to avoid them. For the resistors, I limited them to just 0805 resistors. No real reason, just I found them easy to work with. They're still big enough that they're easy to desolder and solder on, but small enough that they don't take up as much space. Also, this isn't really a rule, but the minimum tolerance I chose is just 1%. I mean, I've been able to find all the resistors within a 1% tolerance with no problem at all, so it's just an added bonus. For the capacitors, I have them all as 0603, but I don't really know why I chose 0603. I think I just did, which, I mean, doesn't really make any sense because they're at 0603, they get more of a pain to solder. But I did. I mean, I should probably, in my later projects, just go higher, like 0805. But I mean, whatever. It's also if I couldn't find a capacitance, like a high enough capacitance in an 0603, I just went up. I think I have a couple 1210s or 1205s on there. So it's just general rules. You can break them. Rules are meant to be broken. Okay, so I guess I'll just get into my schematic. So the software I used to make it was KiCad, which is classic. Everyone knows what KiCad is. It's actually really similar to the software by Cadence, like Capture CIS and Allegro, which is kind of weird considering that everyone I know who used Cadence really doesn't like it. But anyways, so the connector that I decided to use was a JST connector. The specific part number is here. Well, JST connectors are pretty good because they're usually really cheap. And also DigiKey makes pre-crimped wires for them. so you don't have to spend a bunch of money on expensive crimpers. You can just buy pre-crimped wires, and it's very easy to make wire harnesses from that, which is a lot better than I find than using those like male to male or male to female headers. I really dislike those. I just find it makes it really unorganized, especially if you have a lot of pins. And they also have like really thin gauged wire, which doesn't allow you to put much current through it. I don't like them. The first part of the power circuit is the input filter. It's just a capacitor with 2 ferrite beads. I basically just copied this circuit from, I think, an Adafruit breakout board. It was the ADS 1014, I want to say. But it's just to remove any high frequency noise. I think because the impedance of the ferrite beads increases significantly at a higher frequency. It's kind of like if you look at the impedance versus frequency graph, it's like a little hump. So that's hopefully to get rid of high frequency noise. I'm not really sure how well this circuit will work. I only really put it in because it's like each component is like 16 cents. So it's like even if it doesn't work, it's like, who cares? Or like $1. It's under $1 for high frequency noise reduction. Fine. For the filter itself, the only thing I would be concerned about would be if it's drawing a lot of current, there could be a large voltage drop across them. But really, I'm not really expecting anything like that because the board is just a bunch of op amps, which wouldn't draw like a lot. Like I'm just kind of guessing, but probably under 20 milliamps. There's really not much to test with these. I think later on I just saw the voltage drop across them, and it was like nothing. So, I mean, good on you, input filter. For the design, I just assumed that I would have access. Well, I designed it around all 5 volts just because it's a common voltage. There's no like real solid reason why I chose 5 volts, just that it was common. A lot of breakout boards just use 5 volts. Just say, oh yeah, it's 5 volts in, whatever out. It's available, I think, on Raspberry Pis and Arduinos, so it'd be easy to interface with that or use those as power supplies. So, I mean, 5 volts, whatever. There's not really a lot to the circuit. I mean, it fits on one page, but the big part is the charge pump, which takes the input 5 volts and converts it to a negative 5 volts. A charge pump, if you don't know, it's just a switch mode power supply that uses capacitors and switches to boost a voltage. It was cheaper than a buck boost and also uses less components. And also the capacitors, I mean, they were like 50 cents each, so who cares? The charge pump that I went with is the TC1044S from Microchip. Its charge pump is just a variant of the 7660 part, which is just a standard part. I think a lot of companies just have their own version. Dave Jones did a really good video on this. You should watch it. I'll put a link. Maybe not. Google it. I went with this chip over the standard one from Microchip just because it has the option to using the boost pin to switch at a higher frequency. And if you look at the standard equation for the 7660, a higher frequency means less noise, or less amplitude. Yeah, less amplitude in the noise. So I thought that'd be better. I just kind of saw this now, but Microchip even makes a 7660H, which switches at 120 kilohertz. So maybe I should have used that. I mean, it's too late now. I'm seeing this now, but whatever. So the circuit was really easy. I just copied the circuit from the data sheet, which was just like a simple negative 5 volt converter. I think the capacitors used were 10 microfarad 0805 ceramic, which were fine. The voltage rating was fine. So the other chip there you see is just a backup. It's the LM2776. I think actually Dave Jones made a video about that one too. But It was just a backup. Usually when I make boards, I just want to make, since it's like a development board, I just want to make sure that I have a backup in case stuff goes wrong, because you never know what might happen. So for testing the charge pump circuit, I think I just made sure that the output was close to an inverted version of the input. I think I powered it on with 5 volts and the output was -5, so I was okay with that. So since I'm expecting the charge pump output to be noisy just based on the nature of the circuit, I have to put some sort of filter circuit on the output of the -5 volt rail. So there's two things that I was gonna go with, that I was gonna decide between, and that was an LC, just a simple LC filter versus a capacitor multiplier circuit. I actually learned about the multiplier circuit from a DE vlog video, it's a really cool circuit. It basically just decreases the amount of current that goes through the just a low pass RC filter by using a transistor. So in this case I use a Darlington because it has a higher current gain. But yeah, it's pretty dope. I think I forget, but it's basically, I think it's just an emitter follower. So you can use a larger value resistor and capacitor to get a really low cutoff frequency. I've actually never even seen a circuit like this, so I just wanted to include it just to test it out. I ran an LT spice simulation on it, and the thing I was worried about would be the large collector emitter. Is it collector? Yeah, collector emitter voltage drop. I think since it's a Darlington, it's 2 times the base emitter voltage. I didn't really care what the values of the RC filter was, just a really low cutoff frequency, so I was able to find some pretty high 1205 components, capacitors, and combined with like a 1000 ohm resistor, it ended up being a cutoff frequency of around 1.6 hertz, which is actually pretty good. And when you compare it to the LC filter at the top, just trying to choose small components, I think the cutoff frequency was around 2333 hertz. So you can see that the capacitor multiplier, you can get a much lower cutoff frequency easier. So I originally wanted to measure the noise difference between the two, but I don't actually have an oscilloscope. I only have the analog discovery module thingy, which is good, but it doesn't really have a good way to AC couple a signal, so I couldn't really measure the noise, and I ended up just seeing the voltage drop across the capacitor multiplier because I assumed it was going to be better anyway with a lower cutoff frequency, and just assumed that the ripple was way lower than the LC filter. Well, not way lower, but like lower in general. So basically I put a load to draw around 20 milliamps, and as you can see the voltage drop was around this, which I think matches up with the earlier base emitter voltage type thing. I don't know. In any case, the ADC I used was the ADS1013, which has the lower end scale voltage being -2.043, something like that. So basically a -3 voltage negative rail at full load is good enough because no signal will go, or would not go over -2 anyways. The capacitor multiplier circuit works with this board. Which brings us to the end of this video. Yeah, I mean everything works fine, at least the power circuitry. So for the next one, I'll just go over the validation of the op-amp gain circuits and stuff like that. Should be more interesting anyways. But yeah, peace.